Hello and welcome to our expert webinar. The latest generation of high voltage IGBT modules from different manufacturers is becoming increasingly popular. Compactness, efficiency or low leakage inductance, these are just some of the advantages that are prompting more and more users to replace previously used module designs in new developments. In our presentation today, Virgiliu Botan, Global Product Manager for the BIMOS semiconductor products at Hitachi Energy, will tell us how the market for LinPak modules has developed and what options and possibilities the modules with a blocking capability of up to 6.5 kV offer. My name is Eric Rehmann and I'm Marketing Manager at GVA in Mannheim. This webinar is part of our expert series in which we are happy to share our knowledge and that of our partners on new products, technologies and findings from the field on a regular basis. Also check out our website gva-power.de and register for the webinars that interest you. Or simply visit our YouTube channel and watch the video recordings at a later time. During the live webinar, please feel free to use the chat function of our online portal and ask your questions. We will be happy to address them after the presentation. But now we go live to Virgiliu Botan in Lenzburg. Virgiliu, I hope you can see and hear as well.
Okay, so then I take over. Welcome everybody to this presentation. I want to say a couple of words about our products, what we launched in the last period of time, and their importance and impact into power electronics. So it's about high voltage LinPak. If we look a little bit of the portfolio that we have in terms of what we call BIMOS products, so products where we have a MOS structure into the semiconductor. From Hitachi Energy, we have in this diagram voltage against current, this type of products. So we have the classical high-pack standard modules used in traction and medium voltage drives and other applications. We have press-pack IGBTs for very high power devices, 4.5 and higher voltages. And then we have industrial modules like, the classical footprint and EV modules for electrical vehicle. Now, in the last, let's say 7 to 8 years, 9 years, there's a new class of power semiconductor modules. We call them LinPak. They come under different names by different manufacturers. We are proud to say we were the first or among the first to launch this footprint and have it in commercial operation, the low voltage LinPak with isolation up to 6 kilovolt voltage classes, 17 can accommodate also 1200 volt up to 3.3. And more recently, we add to the portfolio the so-called high voltage LinPak that covers IGBT and we'll see later silicon carbide MOSFETs from 3.3 kilovolt up to 6.5 kilovolt, and isolation voltages to 10 kilovolt. And if we look now in terms of application, we have these new devices. We call them LinPak, as we said, low voltage and high voltage. We started commercial operation for this one around 2016 in traction applications for traction inverter. But afterwards, we saw really in the coming years a larger adoption in different industries of this footprint. So we see now wind, photovoltaic, together with battery storage. We see also adoption in mining trucks, in grid application like StatCom, and other, let's say, new application when we talk about hydrogen, industrial heating, even your Hyperloop, all sorts of inverters in mid to high power ranges. So why are these modules so attractive for our customers? Is because they have a compact design. They are in a phase-leg. So if you design a two-level converter, let's say three-phase two-level converters for a classical inverter for electric motor, you need 3 of these modules, and you can realize the functionality of the inverters. You can realize a very compact design. You have in these converters the DC plus minus in a co-planar design inside of the converter, of the module, sorry, which leads to very low can you hear me? Yes. Let me see. Okay. So I get some messages that some people can hear, some people cannot hear. Eric, what do you say? We can proceed, or?
Yes, we have some problems with some kind of browsers. We get green light from this person that have Chrome, for example.
Yeah.
So
yeah.
So I think we can proceed with Virgiliu.
Yeah. Yes. Okay. So continuing on the features of the module. So as I said, compact design. We have as how the module is built also inside with this co-planar distribution of DC plus minuses terminals, and the commutation loop that happens inside of the module, very low stray inductance. That's why this module is, let's say, ready also for even faster semiconductors like silicon carbide. We'll see also a bit later in the presentation. Also, in the same footprint, we can accommodate, as we saw before, quite a large range of semiconductor with blocking voltages from 1200 volt up to 6.5, which gives also the customers the possibility of platforming. So to have one set of, or in this case maybe 2 set of bus bars and let's say heatsink and mechanics for different low voltage or high voltage, but then afterwards cover quite a wide range of voltage classes and power ratings. And then additional to that, being a newer module, newer that what we have in the classical HiPAC modules, we have inside from the processing point of view new features, like for instance the welding of the terminals, really optimized pattern of the bond wire on the top connection, sintering of the chips, which of course gives lower RTH and massively increased power cycling capability. And as I said, the adoption of both silicon and silicon carbide or wide bandgap materials. If we now go and look specifically at high voltage LinPak, this is how 3D blown out looks like. Here we have a small video. I think it's difficult to work right now to see the different components that build up together this module. As I mentioned before, for increased reliability, we weld the power terminals. And what is very, very nice for us, for Hitachi Energy, during this welding, we have a so-called air blade that we blow air under high pressure from the sides into the module at the place of where we do the welding. As you can know, the welding process creates a lot of or creates copper particles when the sonotrode comes above the terminal and is doing the welding process, and this small copper particles, they are we call them hot particles due to the welding process. They are semi fluid, and they flow around when the welding is happening. And most dangerous, let's say, possibility is that they land somewhere that later they can cause a short circuit, or they might land somewhere on the chips, on the junction termination, and so where they disturb the electric field distribution. So this is let's say, from reliability point of view, a big concern. And that's why we at Hitachi Energy, we introduced this process where we blow this air. We have this here, a compression zone, and then it goes with high pressure and blows every possible particle that is created during the welding process. It blows it out of the module and doesn't let it stick around, which then, of course, in the end increases reliability. In terms of footprint, this is our footprint. You find also in data sheets. This is conform with roll-to-rail specification. So we have this committee in Europe tries to standardize power electronics modules, semiconductor, especially for rail application. But then it becomes a standard otherwise. So we follow this type of standard. What is something specific about this module? We have the option from Hitachi Rail to install an NTC, so a temperature sensor on the module. Predestined would be on this chip. On chip we call it number 10. And to be, from the potential point of view, on DC minus. But you can see here, especially for very high voltage devices like 6.5, we kind of come across with the DSAT function when we test this, and we got some suggestions from customers to reallocate this and have the NTC on the AC potential. So right now we are offering this option of NTC rather in the middle, in the AC and the AC potential, to make also the gate unit design for the module easier, and be able to realize a gate unit that is as compact as possible, possibly in one plane for all voltage classes. Let's say 3.3 kilovolt up to 6.5 kilovolt, and still follow the isolation and cribbage and distance requirements. So this is something new that we are also let's say looking forward to further feedbacks from possible customers and the industry in general. But this would be one potential let's say option that we offer that we otherwise don't find it in other modules or with competition. Now, for us in the high voltage LinPak, the first product that we have out there is 3.3 kilovolt device, traction grade, and with a rating of 600 amp. And I will talk a little bit about this product in the coming slides. So here we use a new high voltage trench technology. So what we have so far in high voltage, we have the classical, let's say, planar designs. We have it with ratings up to 1500 amp in HiPAC, and then we have the original trench or the classical trench in also in HiPAC with ratings up to 1800. And this new trench that we now develop for this device, it has some active trench protection. So we know the trenches have from functioning point of view, when you switch off, the danger of let's say affecting the bottom of the trench, the electric of the bottom of the trench with hot carriers. So we do dummy trenches to protect that. We have active plasma flow control, and to demonstrate and to make sure that we have a stable trench. What we do is we intentionally go into dynamic avalanche. So we run pulses, turn on, turn off pulses at let's say SOA conditions. So 2.5 nominal current to 2.5 times the nominal current, 2.5 kilovolt for a 3.3 kilovolt device. And then we apply in this condition under this, let's say, SOA conditions, 100,000 pulses, and we look at the turn-on event and wave curves and the difference in DIDT, DVDT. Because what happens is, of course, if we see a degradation of the if we would possibly see a degradation of the gate dielectric, especially on the bottom of the trench, we would get a change into the gate dielectric, and through that the capacitors change and a change in how the IGBT turns on and in the DIDT. Of course, per se, that is not immediately dangerous, but of course it puts more stress with time over the diode, and in the end can lead to failure. So an internal figure of merit is that we run at least 100,000 pulses, such SOA pulses, and we look at the turn on the DIDT, and this is our limit. So we want to see that this is as stable as possible under these conditions. To show more of these curves, here is an example of extended RBSOA. So we go as high as possible. So you see even 6 times nominal, and the chips still survive this type of high current. So turn off 6 times nominal under against 2.5 kilovolt DC. Also for the diode, we go to also very low RGs to increase the DIDT, to put the diode under stress, and the diode is still soft enough, can cope with this type of conditions. So very robust design. Here some examples of scaling of turn off versus currents or current series, the losses, and you can see also RG influence. So even at higher, of course, higher RG, you can play with RG to make it a bit softer or faster or slower. Even in turn off, of course, turn on, very sensitive to to changes in RG, current series over the temperature range. All of this, of course, available also in the data sheet, and also for the rectifier, for the recovery, for the diode recovery. Current series is, of course, inverse against the IGBT. Couple of waveforms on the SOA, going down to minus 40 degrees. We can see from very low currents up to SOA currents minus 40 degrees, no problem. Then room temperature, quite a soft behavior even at cold, and here also 150 degrees, a current series from 0 to SOA voltage. So all in all, very robust behavior, soft for all the application, even application that might have higher strain inductance. So I have to say this is a 3.3 kilovolt device in high isolation package, which means that can be used also in multi-level converters or 3-level converters where the higher isolation would be needed. And in this type of converters, one would rather have these conditions where the strain inductance is higher or the commutation loop inductance is higher. So this module is very well suited for such applications. We also have, of course, the housing for the higher voltage devices. So here is an example of, let's say, SOA conditions, IGBT turn on, turn off, short circuit. For a 6.5 kilovolt device, we will rate this 300 amp. And here we see also quite a robust chip. In this case, would be a planar chip, but very robust, and the highest current density that we see out there. So I mentioned in the beginning that we have these packages for silicon, but we can put also silicon carbide inside. So examples, what we want to cover with silicon carbide with this package is that, again, in terms of voltage versus current. So we have the LinPaks with the low voltage starting at 1200 volt up to 3.3, and then high voltage with 3.3 up to 6.5, also for silicon carbide. Of course, we have other packages from Hitachi Energy, like the EV packages or industrial packages. And of course, silicon carbide, now it's coming more and more in the applications. There's still question marks on the reliability and design. So the chips, due to cost and defectivity, tend to be rather small in size compared to what we are used to in the silicon world. And that's why also per design, this is an example of low voltage, but it's exactly the same for the high voltage. We spend a lot of time thinking how to make the distribution, the arrangement of these chips, the connection as homogeneous as possible. So gate coupling and normal electromagnetic coupling between these chips is as homogeneous as possible. Of course, you have so many chips that have to work together for the overall switching behavior. Of course, when we put so many chips in a module, it's more complicated than trying to switch discretes, and that's why all this care has to be taken. Also, in terms of reliability, silicon carbide, we know the gate dielectric is a big question mark. So we do a lot of tests, so-called TDDB, time-dependent dielectric breakdown. So we subject the chip to much higher gate voltages and until they break down, and then we extrapolate this type of line lifetime to the gate voltages that they will see in normal operation, like 15 to 20 volt, trying to simulate let's say the reliability of this dielectric in real life. So a lot of work being invested into making these layers as robust as possible. Also in terms of reliability, then we test electrically to see what happens. So you see an example of testing HDRB, 1,000 hours, and then the IV curves before and after. We had an external device that we bought under the same conditions, and had a bit of a surprise in difference in leakage current after this 1,000 hours HDRB. So yeah, we spend a lot of care looking at this reliability aspect of silicon carbide. The same for VTH. This is also quite classical in terms of degradation of the gate dielectric or other let's say degradation that happen in the channel with time, and then we try to observe this what happens after many hours under voltage. Now, when it comes, of course, to performance, because we spent all this, let's say, effort for silicon carbide because it promises very high performance. We see here the current output versus frequency for silicon carbide 3.3, which has what we call full population of the module. It means that on the substrate, on the ceramic substrate, we put as many chips as we can possibly fit. So we fill out the whole area. And the characteristic, of course, of the silicon carbide is that due to the low switching losses, the dropping of the output current at higher frequencies is much milder or lower than compared to silicon. But as we can see here, so if you look at substrate that we say it's half populated, so half a number of chips, it has lower current output, but the dropping at the higher frequency is considerably less, and we see it also for low amount of chips. And this has several reasons. It has to do also with inductance, with the matching of the chips. So the more chips you have, the bigger let's say the spread between them. So the less the homogeneity, how these all chips switch together. You might need to slow them down to avoid oscillations. So in overall, we see that the lower amount of chips you have per chip, of course, strain inductance is even lower, and the switching losses proportionally are lower, which brings back and as a final plot is the current output of a silicon carbide, of a silicon device, silicon IGBT device. So these are mock-up drawings of the substrates with the different chips, more or less to scale, but remember it's still a mock-up. And of course, due to the difference in switching losses, the dropping of current output versus frequency for silicon is much more severe. That is why the question always rises, if I want to use a silicon carbide device, what is the price against a silicon module? And I always have to say, there's no universal answer, because It depends on the application. So if you want to fully populate it with silicon carbide, of course, also the cost is the price difference is quite high. But most likely you don't need to do that because if you want to, let's say, switch at 2, 3, 5, 8 kilohertz and you have a certain current, maybe even 2 small chips above 3 kilohertz will give you a more higher current output than a fully populated silicon. So then and when we compare then these two, of course we have a different cost ratio as we were comparing the fully populated device. That's why for silicon carbide, especially in order to make a larger adoption of that, is very important to look exactly the performance at the desired, let's say, output current, desired switching frequency, where it makes sense to switch it. What are the advantages when you increase the switching frequency depending on the application, and so forth. So right now we have in commercial application a module that looks more like this. So half populated would be this current output line that the customer is switching at 10 plus kilohertz. So they switch in a DC-DC application at very high switching frequency at 3.3, of course, to reduce the inductor. And this would simply not be possible with silicon. So the current output at 10 kilohertz for a silicon module is close to nothing. So that's very, very small. And this we see very well. This is exactly what we did. So we took these two modules. So the module that I showed in the beginning, which we are launching for traction application in silicon. And we put the curves on exactly on top of each other with a half populated module. So from current rating, they are quite similar. So 600 versus 500 or 480. But you can see here the difference in switching speeds, right? Both in terms of turn off and turn on, and also energy. You see here the integrated, so the integration of current and voltage versus time, so the energy of the silicon and silicon carbide, and the same for turn on. And of course, that is this difference in switching energy is the difference between this currents, this current output versus frequency dropping much faster for silicon than silicon carbide. And this type of module in silicon carbide, with silicon carbide half populated in high voltage package, as I said, is now running in trains, in commercial, not a demonstrator or something, but commercial operation, because of this huge difference in switching losses and the possibility to operate at very high frequency. We talked also in the beginning the advantages of silicon carbide, of high voltage LinPak, and then here we see also parallel operation. This is done by one of our customers in traction application, took two high voltage silicon carbide devices, not having a selection or anything, and put them in parallel and run a current series, and the current sharing was amazingly well. So this is also, being a smaller module compared to the high pack, this of course it's a relevant question, how well the parallel operation works, and they are designed for that, and we see also in real life as a result that this works very well. And then this brings me to my conclusions. So I showed you a couple of slides about this new standard in high voltage LinPak. So with isolation 10 kilovolt, which accommodates chips from 3.3 to 6.5, both in terms of silicon IGBTs and silicon carbide MOSFETs right now, which offers the silicon one very soft and robust device, the silicon carbide extremely low switching losses for special applications, and it's becoming more and more now a new standard for high voltage modules. And I hope this convinced you when you have such application to go, let's say, very confidently towards this type of package with both types of semiconductors inside. With this, I thank you for listening and open for possible questions.
Yes, thank you very much, Virgiliu, for this interesting presentation. This brings us to the question and answer session. You now have the opportunity to formulate your open question in the chat. Please make active use of it. And while our guests have time to type their questions, I would have some questions from myself, Virgiliu. First would be, what are the typical applications using the high voltage silicon LinPak?
Yeah. So right now I mentioned, and we have both silicon and silicon carbide in traction applications. So the silicon version is more, let's say, the classical motor inverter application for trains, and silicon carbide more in the DC-DC part. But we see now that we are starting with design-ins for grid applications, let's say StatComs at very high or industrial or grid voltages, let's say 33 kilovolt or so. And there it's very typical that you do MMC topology, so multi-level, and of course the higher the voltage per cell, you reduce the number of cells if you go to higher voltage devices. So that's the attractivity of having high voltage devices there as well.
What is in your point of view still holding back the spread of the silicon carbide version?
Yeah, I think obviously the biggest problem that we have is, especially for high voltage devices, is cost plus reliability. They are to some degree intertwined, let's say combine one with each other, at least in the first phase of defectivity on the starting material. So the thicker, the higher the voltage class, the thicker the epi, the higher the chance of having defects into this layer, and this in turn has a big impact on the cost. And compared to silicon, of course, silicon carbide, the starting material scales quite directly with voltage class, the cost of it, and this makes it, as a first instance, a bit prohibitive to use very high voltage devices, unless there's a payback. And as I said, we have 3.3 being switched at above 10, above 15 even kilohertz, which is unheard of in the silicon world for this kind of voltage class in a normal inverter. And of course, as we manage to reduce cost, as we manage to improve the reliability, the effectivity of silicon carbide, but mostly reduce cost, this will, let's say, broaden the application range that the silicon carbide at these voltages can address.
Okay, thank you. And from your point of view, why is LinPak replacing your HiPak modules or IHM modules in the high voltage applications?
Yes, we already see it, also based especially on the arguments that I brought in the beginning. We see more and more LinPak replacing the IHM modules. Nevertheless, we also have applications where IHM, because it's even a bigger module, also compact. Even IHMs are being switched 2 or 3 in parallel, and then if you switch to LinPak, which is a smaller device, roughly per switch, a third of that, would increase heavily the paralleling, which of course LinPak is good for, but at some point you have to ask, where does it still make sense? So we will see, especially depending on the application, probably in the next 10-15 years, cohabitation of the 2 standards. But I guess more and more the newest chip technologies and the newest, let's say from the processing point of view, manufacturing techniques will be brought more and more into these newer packages, and the IHM, or how we call it, HiPak, will tend to, in my opinion, stay with the standards that we have already. So that's why I guess with time from our customers and the designers will migrate in that direction in time. Yeah. Mm. Also for very high power applications.
Yeah. Will there be even higher voltages than the shown 3.3 kV available in SiC?
Yeah, I mean that's the proposition of silicon carbide, or the promise that we can have 10, maybe even 20 kilovolt devices. I guess at all these voltages, there are the known, let's say, question marks. One being cost that I talked about. Second, availability. In the end they combine with each other. Is it more, let's say, reliable or cheaper in the end at the system level to have a 15 kilovolt device, or we put in series some 3 or 4 of the 6.5 or 3.3. So what is at the end from at the system perspective the more reliable and the cost-effective solution? But of course, there's applications where being compact and reduce the size of your system in terms of, if I'm thinking of grid application of tens or maybe hundreds of kilovolt, that if you make your converter much more compact with much higher blocking voltage devices, can have such huge benefits that can let's say pay the cost of increasing cost of semiconductors. So, but this will have to, I guess, academia is doing a lot of work here. We'll have to together see how this develops in the next years.
Mm-hmm. Okay.
And of course, then we'll need to see what the semiconductors are. Is it probably not a MOSFET? Maybe it's an IGBT, a silicon carbide, and what topologies then are used with such a semiconductor? What is the package that would withstand this isolation, crippages, and everything? So there's still some work to be done. Yeah.
This brings us to the end of our webinar. If you still have any questions, please do not hesitate to contact me or my colleagues from sales directly. You will receive an email with the contact details of our responsible employees afterwards. As experts in power electronics, we at GVA have, of course, even more to offer than semiconductors. In addition to the sale of a whole range of power electronic components, we develop and manufacture assemblies and systems entirely according to your specifications, usually in a range of a few kV up to the megawatt range. Feel free to visit our website for more information. The best way to follow us is on LinkedIn. This is the fastest way to find out the latest news about GVA and its partners, as well as about our latest expert webinars. Virgiliu Botan and I thank you for your interest. I would be happy to welcome you back at one of our next webinars. Take care, goodbye, and hopefully see you soon.